Okay, looking here at the development of the quantum mechanical model, part 1. The main focus on this particular section is really starting with the looking at light and light waves and photons and how from those theories and the different experiments it evolved into the electron and figuring out the position and how the electron cloud looks. That's really what we're talking about here in determining the quantum mechanical model. We'll be focusing mainly on where the electrons are, what does it look like, and all of those kind of features with this. But we won't get really to that electron part until we get to part 2. So this is kind of the build up to getting to there. Learning targets for today. We're going to describe the characteristics of waves and review those. Describe scientific discoveries that led to the development of the quantum mechanical model. We're going to build, like I said, build this process, starting with Planck and quantized energy, talking a little bit about Einstein and the photoelectric effect and what he, theorized from there, and the Bohr model and the line emission spectrum. We are going to do some problems where we're calculating wavelength, frequency, and energy of photons. You're going to find too in this particular section where we're calculating, being able to do scientific notation and those metric prefixes are going to be very helpful in this particular section. All right, starting with the electromagnetic radiation. Electromagnetic radiation, you've probably heard of the spectrum, has a lot of different things on it. I'm going to go ahead and switch over to yellow because I think it's easier to see, but this is all energy that's going to be in the form of waves, and they have wave-like behavior. Okay, travels through space. Now, all types of electromagnetic radiation, these types of energy that travel in waves, they're going to travel at the speed of light. Okay, the speed of light is a constant value. In a vacuum, they all travel at that same speed. The difference is, though, of course I did yellow too soon. Over here you can see the wavelengths. This would be a longer wavelength. And then you can see the next wave here where it's a little bit shorter, and then this one gets shorter. Now we have these funny symbols in here and want to go over what they mean. This funny looking lambda, this is actually the lowercase lambda. It's a Greek symbol, so you can find it if you look in the symbol sections of things. If you look under the Greek area, you should be able to find lambda. And it always represents wavelength. So it is always matched up over here to wavelength. And here, for our purposes for calculating, you always need your wavelength to be converted to meters. And I'll tell you why in just a second. The next feature you should be looking at is the frequency. And the frequency is how many oscillations of the wave are occurring in a certain period of time. So I'm going to switch it back over to something you can see better on this white diagram. So here is a wavelength. Here is a distance period from the dotted line to dotted line. This wavelength's longer, so there's only a couple wavelengths within that same distance. If you look at this one, though, the wavelengths are shorter, so we have a higher number of waves in this particular, so 8 hertz. 8 oscillations of the waves in that particular period. And then down here, you have very short wavelengths where you end up with 16 of those waves in that defined 1 second period right here. And that's kind of important because frequency is what we're talking about there. Frequency in terms of the hertz. How many waves in that particular time frame? Cycles per second. Cycles per second. And it's represented by 1/second. And 1/second is the same thing as hertz. Okay, same thing as hertz. And the last feature that we need to look at is the speed of light, because that's a constant value. As we said, all of these things are traveling at that same speed in a vacuum, so we're going to be referring to that. The speed of light, its variable is always going to be c, and its value is always going to be 3 × 10⁸ meters per second. So this is one of those derived units we were just talking about, meters per second. And it forms this nice little relationship equation here. Speed of light equals the wavelength times the frequency. So the wavelength, which is lambda, the v, which is the variable, v represents the variable for frequency. Wavelength times frequency equals the speed of light. However, since the speed of light is in meters, that's why your wavelength also must match the unit and be in meters. And your frequency needs to be in 1/seconds to match that seconds on the bottom of the speed of light value, that constant value. So we do have to be careful because sometimes they like to give you the frequency in megahertz, or they like to give you the wavelength in nanometers or centimeters or something different. And if they do that, you have to convert it first before you can put it into the equation. One other thing to note, as you can probably visually see over here, is that the wavelength and the frequency are inversely proportional. So what exactly does that mean? That means the wavelength here, as the wavelength is longer, the frequency is lower. The wavelength gets shorter, the frequency goes up. So if wavelength is higher or is longer, the frequency is lower. They're opposite variables. Higher frequency means shorter wavelength. Lower frequency means longer wavelength. Opposite inversely proportional values. Now let's look at it from looking at the electromagnetic spectrum perspective. Here, the longer wavelengths over here, that's going to be your radio waves. Now in between here is also microwaves. Probably heard of those. We all have them in our kitchen because we like to use it to cook food. But, and over here, the very short ones, those are those gamma rays, and we know gamma radiation is high penetrating, very high energy type waves, and high penetrating power, cancer causing, that kind of stuff. I'm sure you're familiar with X-rays, because X-rays, of course, are used to do scans of your bones and things. Ultraviolet, we've all heard that because we need to wear our sunscreen to protect ourselves from ultraviolet rays and not get skin cancer. Those are just above violet over here in the visible light spectrum. Infrared, go on the other side here, just below red. And infrared, I'm sure you've seen in movies where they like wear those goggles where they can see the heat signatures. That would be kind of under that type of radiation. Now this little tiny sliver in here, this very tiny part of this entire spectrum of electromagnetic radiation is visible light, and that's what we can see. And it ranges from purple or violet, which is about 400 nanometers, over here to red, which is, you know, somewhere like 750, to maybe 800 nanometers. So very small range of what we actually can see. And let's correlate here, because we already know that at lower frequency we have a longer wavelength, and at higher frequency we have shorter wavelength. But let's relate that also to energy now. The lower frequency, longer ones are going to be lower in energy. The ones that are higher frequency, shorter wavelengths are going to be higher in energy. So technically energy, if you increase the energy, you're going to decrease the wavelength. So energy and wavelength are also inversely proportional. Inversely proportional. I mean, if the energy goes up, the wavelength goes down. The energy and the frequency kind of correlate together, and they go in the same direction. So lower energy, lower frequency, higher energy, higher frequency. Those correlate together and go in the same direction. For our first example of calculating now, brilliant red colors seen in fireworks. Yes, we all love fireworks. They explode. We see beautiful colors. Well, why are we going to see beautiful colors? We're going to figure that out in the flame test lab. But the red color gives off light with wavelengths around 650 nanometers when the strontium salts are heated. Calculate the frequency of red light of the wavelength that's 6.50 times 10 to the 2 nanometers, or 650 nanometers. Either way you want to write it, it's fine. Now I need to calculate the frequency, and I know my equation is C equals lambda V. So my wavelength and my frequency here I know C because C is always 3 times 10 to the 8th meters per second because that's the speed of light and it is a constant value. Now, before I can do anything else, I cannot just directly plug it in here. This is in meters, this is in nanometers. I cannot directly plug it in there because they're not of the same unit. So I need to go ahead and convert this over into meters before I can plug it into the equation. So I'm going to take my nanometers, I'm going to diagonal them down, and I'm going to go to meters. Does anybody remember the conversion between base unit and nano? So here's our base unit. Okay, then what comes after that? Deci, then centa, then milli. Remember, then it's going to be 2 places in between to get to micro, and then 2 places in between to get to nano. And then if you wanted to finish it off, it would be 2 more to get to pico, because it starts going by 3s, right? So this is 10 to the minus 3, 1, 2. This would be 10 to the minus 6. And then 10 to the minus 9 meters equals 1, and then 10 to the minus 12. So hops down by 3. So you could do it this way. I like to say this is the 1, and then this would be 1 times 10 to the 9th nanometers. So 1 meter equals 1 times 10 to the 9th nanometers. So nanometers cancel, and I'm back with meters here. So I end up getting 6.50 times 10 to the negative 7 meters. You can punch that in your calculator, and that's what you should get. Now that I have it in meters, and the speed of light is in meters, now I can plug it into my equation and be able to calculate from there. So C equals lambda V, so here's 3 times 10 to the 8th meters per second. That equals our wavelength times our frequency. So I'm just plugging it into the formula. Now, how do I get to solve for V by itself now? It's just basic algebra. How do you move that 6.5 times 10 to the minus 7 over to the other side? Divide. Very good. So we're going to divide both sides by this, just like you would in regular math class. So these cancel. They're gone now. The meters cancel too, if you notice that. Meter over meter is going to cancel. Go ahead and punch this in your calculator and divide it out, and we're going to get our calculator answer. And that's why I wanted to really accentuate that you needed to be able to use your exponent keys, because we have to do problems in this section where we really need to be able to do scientific notation. So this is what I'm getting for my calculator answer. Did you get that for your calculator answer? Good. How many significant figures do I get to keep? What is my measured value given in the problem that I need to refer to for significant figures? Yes, this one right here is my given value, and it is 650 with the dot, or they wrote it over here in scientific notation. That means there are 3 significant figures so that I could keep 3 over here. Keep the 4, keep the 6. Do I round the 1 up or leave it a 1? Up it goes. There we go. So ultimately we get 4.62 times 10 to the 14. Now this only thing that's left is the 1 over seconds. 1/seconds or the hertz. You could declare it as hertz or 1/seconds. They are the same thing. This would be your final answer. And then, yes, we have that same answer right here. So that's the first type of problem that you would see using the speed of light equation, relating wavelengths to frequency. Now we're going to do another one. I'm going to have you start it on your own for practice, just like we did this one. It's very similar. A wavelength of a green light from a traffic signal is centered 5.20 times 10 to the minus 5 centimeters. Calculate the frequency. So take a moment to do that. We'll come back in a couple minutes. Yes, before I can begin and sticking it into my equation, I need to convert it to meters first, because it is in centimeters, and the speed of light has to be, meters per second, so we need to have it in meters. So I'm going to go ahead, set up my little T-chart, and convert it. Because we're using dimensional analysis, of course, continuing to practice that. I know it seems probably tedious, but later on you'll really thank me when we get to stoichiometry, because these charts very much so help in the organization of the calculation. They get much longer. They get 3, 4, 5 steps long, and so practicing it while you can is really the way to go. Now, who remembers centimeters to meters, meters to centimeters? What is our conversion factor here? How many centimeters in a meter? Yes, 100 centimeters equals 1 meter. Now the centimeters will cancel, and so we'll end up with 5.20 times 10 to the minus 7 meters. Now we're ready to plug and chug. That's what my good old calculus teacher used to say back in high school. We're going to plug them in and chug out the answer. So we can put in our wavelength here, times 10 to the minus 7 meters, times the frequency. That's going to equal the speed of light. Speed of light is constant, so it's always going to be 3 times 10 to the 8th meters per second. Then all you have to do is your simple division here. Divide, okay, both sides. Now you don't have to technically write this part out on your paper as part of the work. I just need to see the setup, the plugging in of the equation, and then you could crank out the answer. So you really don't have to show me this division step. I'm just showing it for those that need the refreshing aspects of algebra, need to recall these steps. All right, so meters cancel. Then when we do this, how many significant figures will we be allowed to keep in our answer? Yes, only 3. That is exactly right. And it looks like this is what I'm getting for my calculator answer. Getting 5.769 times 10 to the 14th. So I'm going to keep the 5, keep the 7. Do I round the 6 up to a 7? Yes, very good. Round that up. So we get 5.77 times 10 to the 14th hertz, or you can write it as 1/seconds, like that. Either or, it would be the correct answer. Are you following me so far? Because it's going to get just a tad bit, a little bit more challenging here in just a second. Got a firm grasp of this equation and formula. We got to really kind of make sure that we can plug in the variables and we can do this. Now we're going to talk about Planck. So basically, before Planck, came up with his theory, everybody in the scientific community believed that matter could just absorb and emit any amount of energy. Like it was a gradual thing. Doesn't really matter. Kind of like here, this would be a continuous fashion over here, just going up the ramp, okay? Whereas Planck came along and he started really looking at different things he saw and way that he saw that matter was absorbing energy. And he decided, based on his data and observations, that matter can only gain or lose energy in small specific discrete amounts. They're called quantum or quanta. Quanta is plural for quantum. Now, you want to think of these small discrete energy amounts as sort of like staircase. Okay, it's not a lot, but each one is a certain amount. You cannot get to the next stair, like it's all or nothing. You either have to absorb it all to get to the next stair. You can't go halfway up a stair. So that's what we're talking about. We're talking about quantized energies, more like the staircase. You have to reach the next level. It's all or nothing. As opposed to here, if you're on a ramp, you can just slowly work your way up and you don't have to worry about getting over a step. So from his particular observations and data, he derived an equation, the energy equation. So we have E equals H times V. New variables here, except for one is still the same. Which one is still the same as one we already learned and know about? Frequency. So yes, V is still frequency here. Now E, you probably have already, predicted that E is going to mean energy, since that's what we're talking about here. We're talking about energy. H is a constant. It's called Planck's constant. And it's this value, 6.626 times 10 to the minus 34 joules times seconds. Okay, joules times seconds. Now, I do not expect you to memorize Planck's constant. It will be provided to you in your problems when you're given a test or quiz. You will not have to memorize Planck's constant. However, it is a constant value, and we always plug it in here for H into our equation. And there was a bunch of math, when we say these constant values in chemistry, a bunch of math and a bunch of testing went into deciding that this factor is always constant. All right. So now we're going to look at doing a problem where we have to figure out the energy. So blue color in fireworks is often achieved by heating copper 1 chloride or CuCl at about 1200 degrees Celsius. When the compound emits blue light having this wavelength of 450 nanometers, what is the increment of energy, the quantum of energy that is emitted in that process? So basically what happens in fireworks, they have the compounds in there and you give it the heat, which, with the explosive gunpowder in there where it's going to explode. When it gets hot enough, it absorbs and releases energy. And in the process of the releasing of the energy that it absorbed, it gives off the color of light. And that's why we're going to see blue here. Told us, though, the wavelength of the blue light that we see is 450 nanometers. And we want to know the energy. The energy. We don't want to know the frequency this time. We want to know the energy. So we have our two equations we get to work with. Our speed of light equals the wavelength times the frequency. And now we have our energy equals Planck's constant times the frequency. So in order to be able to find E, what do we need to find first here? We need to find V. Yes, we have the wavelength here. We have this value. That's what's right here in the problem. We know the speed of light is 3 times 10 to the 8th meters per second, because that's always constant. So if we find V first, then we can put the V inside this equation. We know Planck's constant is 6.626 times 10 to the minus 34, and then we're able to solve for energy. So I'm going to start by here working with my nanometers. Now, once again, the nanometers is a problem because I can't use it directly in my speed of light equation. I need to change it to meters first. So nanometer is going to go on the bottom, meter is going to go on the top. Now, if we remember from the first problem, 1 meter equals 1 times 10 to the 9th nanometers. So we can quickly convert this over, and we get 4.50 times 10 to the minus 7 nanometer. I mean, not nanometers, meters. Let me change that because we're trying to get meters. There we go. So equals 4.5 times 10, times 10 to the minus 7 meters. Now that we have meters, we can plug it into our C lambda V equation. So we get 3 times 10 to the 8th meters per second equals 4 times 10 to the minus 7 meters times our V. So what do we get for V here, guys? And you can go ahead and round it to your 3 significant digits. So what do we get for our V? Anyone? Anyone? Oops. What do we get for V? Yeah, that's right. Good. 6.6 times 10, or 6.67 times 10 to the 14 hertz, or 1 over seconds. Very good. Now that I know that, guess what I can do? I can just use my energy equation now. And energy is going to equal Planck's constant, which is that 6.626 times 10 to the minus 34 joules times second value that's given to you. That is the constant. And the frequency now I know is 6.67 times 10 to the 14th, 1 over seconds. I'm putting it in as 1 over seconds so you can see that seconds would cancel here. So the seconds here cancel, and then we're ending up with joules. So whatever we get over here for energy is going to be a certain amount of joules. And joule is the metric system unit or international system unit of energy. So go ahead and calculate that, 6.626 minus 34 times 6.67 to the 14th. Now it should be somewhere in the times 10 to the minus 19, which it is. My calculator answer is 4.4195 something times 10 to the minus 19. Now we're going to base it off of our measured value because we calculated that from our wavelength over here. The constants like speed of light and Planck's constant, we do not use those to determine significant figures because they are constant values. They are not measured values. So here we go. We're going to do 4.42 times 10 to the negative 19 joules. And that's a very small, tiny amount of energy, but it is that particular quantum amount of energy that was absorbed to be given off by the atom that gave off that blue light in the firework. So then you see the pretty blue in the sky. Small amount of energy in order to give off 1 photon of that blue light. Now, of course, in the sky, you see many photons of the blue light, so this value would be magnified, but we're really looking for it just for the 1 photon. And that would be the correct answer. Yay! Okay, I want to show you one other thing real quick, because some of you people are really great math whizzes. I want to show you a way to make this go faster. Now, if what I do here completely blows your mind, you can go and do, I call this the long way. You can do the long way, where you do both equations like so, plug and chug, you'll still get the correct answer. Call it the long way. However, you can do it the short way, and this is how you do it the short way, is you manipulate the equations. Because we have the speed of light equals lambda times v, you have the energy equals Planck's constant times v. Well, they both have a v in them. So that means I can substitute. Has everybody heard of substitution here? Yes, right? So basically what I can do here is I can manipulate my equation. I can divide both sides by lambda, right? So I get C over lambda equals V. What can I do now? I can take this C over lambda and I can stick it in for the V. So energy equals C times H over lambda. If I do that and I substitute, now I only have to deal with the one equation. And I could just plug in, I could put the speed of light times Planck's constant divided by the wavelength is going to give me the energy. Does that make sense? Hopefully it does. I mean, I'm hoping you would impress your math teachers by realizing that the substitution thing, we can do that in science too. And it makes it a lot easier and more time efficient. So if you're getting what I'm talking about here with the substitution, feel free to use it. Okay, just show me that you're substituting, you know, you're combining the equations and doing the substitution, then you plug in your numbers and you can go from there. Okay, so that was just like a little added, you know, tricks of the trade here, speeding things up. I like to work smarter, not harder. Okay, so this is a fun one. This one you can't really do what I just told you to do because look what they want. Calculate the energy and the wavelength in nanometers for a photon of light that has a frequency with a frequency of 6.165 times 10 to the 8th megahertz. Oh, I can see a problem here. Anybody else see a problem here? Can I just go right into my equations? Is that possible? What's wrong with that frequency? It's in mega. We need the frequency to be in what? We can't put it in our equation if it's in megahertz. We need it to be in just hertz. Like hertz would be the base unit. So you need to do the mega change over to hertz here. Does everybody remember the mega? Because here's your base unit, right? Above the base unit, we have deca, we have hecto, we have kilo, right? So this is going to be like 10 to the third. Then 1, 2 is mega. So mega is 10 to the 6th. So there's 10 to the 6th base units in 1 mega of that unit. So really 1 times 10 to the 6th hertz equals 1 megahertz. So you're going to have to do that conversion before you begin. So go ahead, take a moment, try to solve the rest. I gave you a head start here. Try to solve the rest. We'll come back in a couple of minutes and work the rest of the problem, and you can check your answer. Okay, let's go ahead and work through this. Hopefully you've had time to process here. Calculate the energy and the wavelength. So it doesn't really matter which one we start with. I'm going to go with energy first since it listed it first in the question here. So first of all, changing this over megahertz to hertz. So 1 megahertz equals 1 times 10 to the 6th hertz. And therefore this is times 10 to the 8th. So then you end up getting 6.165 times 10 to the 14th hertz. Megahertz cancel, and we end up there getting that value. Now we can plug and chug. We get our E equals HV. So energy is going to be equivalent to 6.626 times 10 to the minus 34 joules times seconds. And that's the given value. Remember, you just always use that for Planck's constant. You know, have your notes out, use that for Planck's constant. I'll be putting it in the problem if it's a quiz, though. So you'll have Planck's constant listed there for you. And then we enter in our frequency, 6.165 times 10 to the 14. I'm going to put it in as 1 over seconds so I can cancel my seconds here. I do that calculation. And this has 4 significant digits in its original measured value, and I'm going to keep those 4 as well. Oops. So I'm getting 4.08 times 10 to the minus 19 joules. So this would be the energy. That would be equal to E. That part's done. So I did check that off my box of answers to do. Now I'm going to go ahead and look at the other one here, looking at doing the wavelength. In which, I'm going to use the other equation, that C equals lambda V equation, to solve for wavelength. So 3 times 10 to the 8th meters per second equals lambda times our frequency, which is 6.165 times 10 to the 14th hertz, or 1 over seconds. In that case, then that's going to flip when we divide, so they will cancel and we'll end up with meters. 3 divided 3 to the 8th divided by 6.165 to the 14th. That's going to give me lambda equals 4.87 times 10 to the negative 7 meters. Now this gives me meters, so I'm still not done yet because it really wants it in nanometers. So I have to do one more step, which would be converting it into meters. So 4.87 times 10 to the minus 7 meters. And then put the meters down there, go to nanometers. So 1 meter equals 1 times 10 to the 9th nanometers. When that's all said and done, looks like it's going to be like 487 based on what I can see about the powers here. And yes, your final answer when you calculate this, lambda should be 487 nanometers as that final answer. So yeah, these problems take a little bit to get used to, and they're new variables, new things to work with, but we're measuring very small particles because you're measuring photons and things like that, their energy, their wavelengths, and their frequencies. So very small measurement values that we're dealing with, except for the frequencies are big, because frequency times 10 to the 14, that's a big value, especially if you have a short wavelength. Keep in mind, it's going to take a little bit to get used to, but you'll do some more practice problems of these in that flame test lab when you're doing that. And then hopefully it's pretty much the same pattern though. So once you got the pattern down, it's not going to change too much. Good. Oh, wait a minute. I didn't do the significant figures right. Yay. Okay, I feel dumb now. None of you even questioned me. You guys need to question me. I rounded to 3, but why did I round to 3 when there's 4 over here? I don't know, because I wasn't paying attention. So this should be 6 times 10 to the minus 7. So that means this should be 6 times 10 to the 7. So this is now, let's fix that too. Oops, I erased that too. Here we go. All right. 486.6 nanometers. See, even I can sometimes not pay attention to sig figs. There you go. There you have it. There's your answers. This will be posted later on to the video so you can watch it. Be able to go back over the steps if you're a little confused. Okay. Continuing on with the photoelectric effect. Photoelectric effect, something proposed, studied by Einstein, and he used Planck's interpretation of how energy is quantized to explain the photoelectric effect. So the emission or ejection of an electrons from the surface of a metal in response to light is really what the photoelectric effect is. So that's what we're talking about here, is like shining light onto the metal, and electrons, of course, are getting ejected. And that's what is showing up here in this part of the picture. Okay, energy hitting the metal's ejecting electrons. Now, light below a certain threshold frequency, no matter how intense, did not eject the electrons. So we're talking about things with lower frequency, which means they have longer wavelengths. Those ones did not eject the electrons, like red light is lower frequency, longer wavelengths. Red light would not eject the electrons from the surface of the metal. Light above the threshold frequency, even though it's not very intense, did always emit the electrons. They always were being jumped off. This would be something like the shorter wavelengths like violet light. They have higher energy, higher frequencies. That one was capable, it met the threshold and was able to eject the electrons from the metal. Now, what does this mean? Therefore, the energy equals Planck's constant times the frequency. Basically, applying that equation here to the ability to eject electrons from a metal surface. This also is we'll touch back on this later, but it's going to kind of go to the idea of the wave-particle duality of light, and that we used to think of light and energy, electromagnetic radiation, as just only being pure energy. But the fact that it's hitting a surface and then ejecting electrons kind of gives the idea that there is some sort of hard little piece of matter in there. And that kind of gives it the idea that it has this particle behavior as well. So wave-particle duality now is starting to be looked at in terms of photons and photons. So instead of just calling it pure energy light, we call it photons because they're like waves of little particles of light. And if they have the ability to eject the electrons, they must be made of some kind of matter of some sort in order to do that. So that's another little aspect of the photoelectric effect we'll touch on here at the end. But basically what we're seeing here is the amount of energy. There is that threshold energy, that packet quantized amount of energy that you needed to meet that threshold. You needed to make it above that step, or it did not eject the electrons. Now, talking about the different types of spectra, and we're mainly going to be focusing on these two spectra over here, the continuous versus the emission. Absorption, we don't pay a whole lot of attention to at this particular juncture of chemistry. But the continuous spectrum really is just white light being shined through a prism, where it definitely diffracts it based on its wavelengths. So you get the nice, beautiful rainbow colors. The emission spectrum, though, as you can see, is mostly black with a few colored lines in it. We're going to talk about why it has those few colored lines. So the continuous spectrum, once again, you just basically take white light, you put it through the slit in the prism, and it breaks it apart into the rainbow based on wavelengths. So red over here is going to be the longer wavelengths, lower energy, and then the violet over here are the shorter wavelengths with the higher energy. Okay, so shorter wavelengths. That's all the continuous spectrum is. It's this nice, beautiful rainbow. But we like to look at it because it's kind of a comparison. It's like the base model here. We're talking white light. Now, for emission spectra, though, they were being studied a lot in the early 20th century, early 1900s. Scientists were observing how different atoms and molecules were emitting light, emitting energy. Now, this is the gas tube setup, and you're going to see it in the flame test lab as well. Basically, it's this narrow tube, and inside has atoms. We only have elemental gas tubes. So you stick it into this little box, and it completes the circuit, and you can turn on the electricity, and then you give it energy, and it lights up. And you can see the orange neon gas here in the middle when it lights up, when it has electricity. So we're providing those neon gas particles in their energy, and they're lighting up. Now, what they were studying this and figuring out that it was related to the arrangement of the electrons in the atom. eventually heating it, looking at how the electrons were behaving in that electron cloud and how were they arranged in that electron cloud. So we're going to study some emission spectrums in the flame test lab as well to give you a little bit of idea of how that was utilized in interpreting and producing the quantum mechanical model that we have today. The line emission spectrum, looking here at the line emission spectrum, basically what you see is the gas tube will go through the slit in the prism. Here it's giving off a continuous spectrum. But if I just have hydrogen gas particles in the tube or neon gas particles in the tube, when you look through the screen there, you will only see a few, well, for hydrogen, you only see 4 colored lines. Now that's because hydrogen is the most basic atom that we have. It only has 1 electron. So it doesn't have many different electron transitions or electronic transitions. It only produces 4 different colors of light when it's given energy. However, neon, as you can see below here, has many more lines and many more pattern, but that's because neon actually has a lot more electrons than hydrogen. Neon has 10, so definitely a bunch of different more combinations of ways the electrons are behaving here to produce these many colors of light in its particular emission spectrum, line emission spectrum. Now these are like fingerprints for the atoms because it is distinct for each particular atom. The pattern, each particular element has its own pattern as to how these lines come out when the gas particles are given energy. So each one's individual to the element. Hydrogen won't look like neon, neon won't look like carbon, carbon won't look like oxygen, and all of that. They'll all be different in terms of their lines on the spectrum. So comparing to the continuous, which would be up here, we're looking at hydrogen and neon in this particular example for our line emission spectrum. When we put the gas tube in, turn it on, we look through the slit, we can only see these different colored lines. All of the rest of them are blacked out. So that means the electrons are behaving in a way where they're absorbing and releasing energy. In order, when they absorb the energy, they end up getting excited, basically. We're going to talk about that too in a minute. But when they fall back to their original configuration, they give off the energy they absorbed. Now, the energy that they absorbed is equivalent to a certain wavelength. We know that through our equations that we were just calculating. The certain wavelength corresponds to the frequency. The certain frequency is going to correspond to the certain energy that was absorbed. So the energy being released by the electron shows us the color of the photon, and the wave that corresponds to its wavelength. And then the wavelength, of course, will also give us the frequency information and let us know we can calculate the energy from there. So lots of different things going on in the line emission spectrum.